Hello, chemist and biochemist. In this video, what I'd like to talk to you about are saturated and unsaturated fatty acids. So, in addition to talking about them kind of simply, I'd also like to talk to you about how they change, or the composition of a membrane changes based on temperature. I'm going to bring up a paper regarding that. But let's go ahead and get started. We have fatty acids, or our fatty acids fall into two different categories. They're saturated and unsaturated. Now, when we talk about a saturated fatty acid, we are talking about a fatty acid that has 0 double bonds, compared to an unsaturated fatty acid, where we have at least 1 double bond. And one thing that I want to go ahead and clear up now is the double bond within the carboxylate ion doesn't count in this numbering or designation. We're talking about a saturated fatty acid having no double bonds within that long alkyl chain, and an unsaturated fatty acid having at least 1 double bond within that alkyl chain. So that's one thing to remain kind of aware of. Now, our nomenclature for a saturated fatty acid would be something like this: C16:0. This would be the nomenclature, or this would be the way of identifying a 16 carbon long fatty acid with no double bonds, whereas an unsaturated fatty acid of the same length with a single double bond would be C16:1. Now, this doesn't tell you anywhere where that double bond is. And for that, what we do is we look at the omega or delta numbering scheme. There are also polyunsaturated fatty acids, so more than 1 double bond within that alkyl chain. So C16:2 would be an example of a polyunsaturated fatty acid with 2 double bonds. Now, this isn't particularly I guess, important, but there are some trends that you notice there are some trends that can be observed within fatty acids. So if we talk about saturated fatty acids, the melting point of a fatty acid is going to go up as the number of carbons goes up. Okay. Now, the same is true for an unsaturated fatty acid. However, as the number of double bonds increases, the melting point goes down as, I'll just say, double bond number goes down. And in large part, this is because a saturated fatty acid, let's go ahead and use I'm going to draw a very crude representation of an alkyl chain of a saturated fatty acid. Well, if you have multiple saturated fatty acids, they can pack very tightly together. And in the same space that, say, these 4 saturated fatty acids occupy, if you have 1 unsaturated fatty acid within that same grouping, so let's go ahead and say here's our saturated fatty acid, and then we have a mixture where we have a single unsaturated fatty acid is found. Well, what that's going to do is basically kind of disrupt the close packing that saturated fatty acids can observe because of the hydrophobic effect. This single double bond or multiple double bonds is going to cause these saturated fatty acids to kind of be separated from one another. And so when you have, like, if we have purely mixed, or we have pure mixtures of saturated fatty acids and unsaturated fatty acids, well, you're going to see as the number of carbons increases, so too does the melting point. As the number of double bonds increases within unsaturated fatty acids, your melting point is going to go down. Now, when you have a mixture of saturated and unsaturated fatty acids, ultimately the overall number of your unsaturated fatty acids is going to play an impact with respect to that melting point. Now, to visualize how that impacts an organism kind of on a uh, or how that impacts an organism as opposed to simply thinking about the molecules, what I want to do is I want to show you this paper right here. I'm going to share, and here's our paper. Okay, so this paper was written in 1962, and it is titled The Effect of Temperature in the Composition of Fatty Acids in Escherichia coli. So simple bacteria was grown. Um, and basically, what the researchers did was, I'm going to scroll down to arguably the most important figure of this paper. What they did was they grew E. coli at 10, 15, 20, 25, 30, 35, and 43 degrees Celsius. And what they observed over time was the number of saturated fatty acids and unsaturated fatty acids changed. So if we look, these first two fatty acids that are listed, myristic and palmitic acid, I'd like to draw your attention first to the lowest temperatures. Whenever we were growing this E. coli at 10 degrees Celsius, what we saw was that the saturated fatty acids, myristic acid is 14 carbons and palmitic acid is 16 carbons long. Both are saturated fatty acids. Those accounted for about, we'll call that 23% of the fatty acids within that organism that were accounted for. Meanwhile, what we saw whenever we were growing, or when we analyzed the polyunsaturated fatty acids or the unsaturated fatty acids, they accounted for more than 60% of the total fatty acids that were accounted for. So at lower temperatures, we have a higher abundance of our unsaturated fatty acids, which our unsaturated fatty acids at lower temperatures are more likely to be liquid than our saturated fatty acids, whereas our saturated fatty acids are more likely to be liquefied at higher temperatures. And so what is shown here, or what these researchers discovered, was that whenever they went up to 43 degrees Celsius, the saturated fatty acids, the myristic acid and palmitic acid, accounted for 55% of the total fatty acids, compared to 22% at that very low temperature. And so then at the lower temperature, they had less of a need for, or sorry, at a higher temperature, they had a lower need for these unsaturated fatty acids to get the membrane to be kind of a fluid system. They were able to acquire that, or they were able to get that fluid system because of because of the higher temperature. Now, the way that I like to think about this is the membrane's kind of fluidity and mobility was basically the same at 10 degrees and at 43 degrees Celsius, but the cell was able to make sure that they were the same effectively by reallocating or emphasizing the production of different fatty acids. So at lower temperatures, we favored unsaturated fatty acids. At higher temperatures, we favored going more towards saturated fatty acids. So you see that melting point, the higher the melting point, or whenever our melting point was higher, then we could use those saturated fatty acids, or whenever our organism was grown at a higher temperature, we could use those fatty acids with those higher melting points. We didn't need to produce a higher percentage of the lower melting point unsaturated fatty acids. All right. Well, I think this is a really good paper, and I think that's an effective one to look at how an organism is going to respond to environmental conditions and produce molecules that make up their membranes at different temperatures. All right. Well, I hope that was helpful, and I hope you have a good one.